I'm Deqing. I'm very glad to talk about our work on optical flow, and its joint work with my colleague Xiaodong Yang, Mingyu Liu, and Yan Kos. Optical flow is a 2D image motion from one frame to the next, as shown in this color representation. So the goal of optical flow estimation is to estimate a 2D real-valued motion vector for every pixel in the first frame. Recent influential work is FlowNet 2, which shows for a fully end-to-end CNN model, it can perform very close to the state-of-the-art. So here the y-axis is the endpoint error. The lower the better. You can see the gap is very small. But if you look at the running time, it's much faster. But looking at the figure, you may wonder whether it's possible for a fully end-to-end CNN model to outperform state-of-the-art, traditional, well-engineered system. So let's look at all the published CNN models for optical flow. So in terms of the performance and also the model size, the number of parameters, you can see there's a clear trend between the performance and the model size. It seems like we need a much bigger model than FlowNet 2, which is already pretty big with 160 million parameters. And surprisingly, I will present PWC-Net, which is very compact compared to most models, but it's very effective. It actually outperforms the published state-of-the-art. So what's the secret? And the secret or the insight is to build what we know about optical flow. That's the domain knowledge into the network. So what do we know about the optical flow? And you may still remember the optical flow constraint equation from your computer vision class. It's derived from this brightness constancy assumption. The idea is a pixel will retain its brightness or some property over time despite its position change. And based on this idea, we can use a very simple algorithm to get some intuition. So for every pixel in the first frame, we can crop a patch. And then we can compare according to every possible motion vector, the corresponding patch in the second image. And we can use, for example, normalized cross-correlation to get this cost volume for this pixel. So cost volume is a very widely used concept in stereo matching, where you can compare along the 1D line. And the nice property here is you can see the peak of the cost volume gives a very good indication of the correct motion vector. And some nice property is it has some invariance to the lighting, to the color change. For example, if the image becomes darker, brighter, the position of the peak remains very constant. But there are also some problems with this very simple algorithm. The first problem is scale. For example, for this patch, you can see there are many similar patches along this line. So it's ambiguous. And so we need a very large context, for example, to get the motion localized. And another problem is this algorithm is very computationally expensive. So for every pixel in the first frame, we need to compare with all the possible motion like in the second frame. And so how can we deal with these two problems? So let's see some great ideas from the literature. And the first is pyramidal processing, which is commonly used for optical flow. So as you can see, when we build an image pyramid, at a small image size, the motion is much smaller. So that's easier to estimate. And also because it's small, we can use a much smaller search range for the cost volume. And here is where the CNN end-to-end approach can help. We can build a feature pyramid to learn the features for the matching. And at the top level, at a small scale, we can get very global context to do the matching. And so let's build the idea into the network. I will use just a two-level pyramid to explain the idea. Given the two-input image, we can construct the feature pyramid. And this one is very small scale. And then we can construct the cost volume by comparing features of the first image to features in the second image. Because the motion is very small, we can use a very small search range. And then given the cost volume, we can give it the cost volume features of first image to a flow estimator, which is a multi-layer CNN network that projects the input to the optical flow. So given the flow estimate in the first frame, in the small scale, we can upsample and rescale to the next level. So now the question is, we have both the upsampled flow and features of the two images. How can we reuse the upsampled flow? And here is another great principle from the literature called warping. And I will use this image to explain the idea. So given the upsampled flow, we can just warp the second image according to the flow field. This gives us the warped image. And the motion between the warped image and the first image is much smaller. So that's easier to estimate, and we can use a small search range. So to give you some intuition, this is an illustration. So you can compare the first image, second image. First image, warped image. You can see the motion is much smaller. So going back to our network, so given the upsampled flow, we can warp the features of the second image. And then we can use the warped feature to compute the cost volume with features of the first image. Because warping makes the motion much smaller, we can use a very small search range. And then we give the upsampled flow, cost volume, and feature of the first image to the flow estimator to refine the motion. And if you consider the motion at the top level is 0 for initialization, the processing will be the same across the pyramid levels. And so the PWC net used 3 great principles: pyramid, warping, and cost volume. You may wonder how much each contributes to the performance. So we performed this study. So we trained the models using the flying chairs dataset and tested on the Intel training set both the clean and the final pass. This is a full model using all the 3 principles. This is the endpoint error, smaller, better. So the first test we do is we replace the feature pyramid with the image pyramid, and everything is the same. And we can see there is more than 30% drop in performance. And another test is we remove the cost volume. So we just give features of the first image and second image to the network. Again, there's like a more than 10% drop in performance. The last thing is remove the warping operation. We just construct the cost volume using features of the first and the second image. And again, there's a more than 10% drop in performance, especially in the final pass. It's close to 20%. And one thing to note is we are not the first to use this principle to build the network. And SpyNet and FlowNet 2 use some of the principles. For example, SpyNet constructs the image pyramid. And FlowNet 2 uses a 3-level feature pyramid in the first module of its big network. But PWC net, we build a 6-level, much deeper feature pyramid. And for the warping operation, so SpyNet and FlowNet 2 apply it to the image. But PWC net apply it to the feature pyramid. And so the information can better propagate through the whole feature pyramid. And the last thing is for the cost volume. SpyNet does not have cost volume. And FlowNet 2 just use it once in the first module of its big network. And so by making more frequent and fuller use of these great principles, we can build a very compact network that outperforms state-of-the-art. And this is the Intel final pass public table at the time of submission of our paper to CVPR. PWC net was top ranked. And if you compare the performance and the accuracy, it does not only perform the state-of-the-art, but also the running time is much faster. It's about 35 frames per second on NVIDIA Titan X. But there are some very critical details. And if you have read the first version of our archive paper in last September, and also compare with our CPR submission, you will notice there is a more than 10% improvement in performance. I think some of you already asked me this question. But the network is the same, so what's the difference? And here are some secrets. It's like the data augmentation is very critical when we have very limited training data. So we need to do careful data augmentation for this like a 1,000 image pair. For example, adding the Gaussian noise during the data augmentation does not make much sense. First, because the Intel data is very clean. And even for the final pass that has noise, the noise characteristic is different. And another good technique is to add the horizontal flipping. So that's a very effective way to increase the training data and improve the test performance. Basically, to deal with overfitting. And this is the KT15 public table at the time of submission. Again, it was top ranked, and it was only worse than thin flow method that used stereo input. That means more information. Again, this is on the robust vision challenge. And something I learned from the process is what makes it more robust. For example, when the training and the test data set do not have much overlap, it helps to use more diverse data sets. For example, compare with training just using the Intel training data set. If we add KT and HD1K, we see some concrete improvement. But during the process, I learned actually PWC net is not as robust as I hoped. It still makes a lot of mistakes. For example, for this input, you can see there's a big error for this object that moves out the image boundary. But I would argue this is a case where the information is not sufficient within 2 frames. So for example, if you look at more frame, you can see this is a case where you can propagate information over time. And another case PWC net fails is for small and very fast moving objects. For example, for the arm, it still fails. Another case is for strong like a reflection that's not consistent over time. You can see there's a still big error as indicated by dark red in this region. And another case is PWC net is still not very good at recovering the very fine motion detail. You can see compared to the ground truth, it can recover up to some degree, but still not perfect. It's still far from ground truth. So this is a very hard case from the Intel test set. The average error is close to 40. But if you look very close to the sequence, you might notice actually there's a 2-layered motion. You have the snow floating in front of the background. And in the evaluation, the motion of the background is regarded as ground truth. But the PWC net is trying to do 2 things to get both the motion of the snow and the background. But this is a case where like a layered approach will make better improvement. So there are still many questions for PWC net, a lot of work to do for optical flow to improve the accuracy. But if we look beyond, there are more questions for optical flow. For example, does the flow accuracy correspond to better application performance? So what makes a good optical flow for a particular application? Should the criterion be application specific or generic? And should optical flow be solved jointly with other tasks like stereo, C-flow, action, video, super resolution, video interpolation? So to encourage discussions on such questions, we are organizing this What is Optical Flow For workshop at the ECCV. And so you are very welcome to participate in the survey and also submit your paper. There will be a high-end NVIDIA GPU for the best paper. So now I'm going to show you some result of applying the two-frame PWC net to the whole video sequence. Although it's a two-frame method, most of the time the results are pretty stable. This is another one on the KT tracking sequence. Okay. So now I'm going to draw conclusions from my talk. So I have presented PWC net, a very compact and effective model for optical flow. The insight is to take these great ideas from the literature and build into the network. But I have to admit we haven't used all the great ideas. For example, oriented smoothness or layered approach. And I feel like there are a lot of hidden gold in this great vision textbook. And if we take this insight and build into the network, it's very likely we can get even smaller and more effective network for optical flow or other vision tasks. And finally, our cafe and PyTorch code will be available at this GitHub address on this Thursday. And that's all for my talk. Thank you.
Thank you very much, and we have time for multiple questions. Rick.
Yeah.
Deqing, that's beautiful work.
Yeah, thank you.
I had one question about the warping. If at the coarse level you have a strong motion discontinuity, then the coarse level will tend to latch onto the foreground or the background motion. So after the warping, if there's any error, or isn't it possible for the first warping stage to get a small band of pixels wrong because you sort of latched onto the wrong thing? And wouldn't the residual motion then be quite large, right? Yeah. And since you're only searching over a small range, how do you fix that?
I think PWC net currently cannot fix that. The later network may try to do something to recover the motion, but if you look at like the failure case for the small for this arm, this is like exactly the case you because the motion of the arm will be lost at a very coarse level. So this is something PWC net still cannot deal with very well. I think some possible solution could be you have separate network to deal with small and larger motion and fuse the motion together. Yeah.
Right. Yeah. I mean, I was thinking of just the first case where you had the car moving. Yeah. That after the warping, unless the coarse level is perfect and your interpolation is perfect, there might be a small band with the background that got moved by the car or vice versa. In other words, I'm worried that there's this idea that the coarse level automatically reduces the residual motion error to a small amount, because it seems like places where it was mispredicted would still have a large amount.
Yeah, I think for this one, the PWC net has some built-in mechanism. So recall, we construct the coarse volume, right, around the warped image. Mm-hmm. The coarse volume is not just it has some range. For example, it's the 9x9 neighborhood. So that can allow for some adjustment.
Yeah, thank you.
Yeah,
yeah.
Thank you.
Hi, I also had a question about the warping.
Yeah.
In the example that you showed with the car, it seemed like basically the warping was correcting for the motion of the camera taking the image, and then the primary change in the image that was left after the warping was just the image of the moving car that you were seeing. So it seemed like in a case like that, the warping was primarily accounting for ego motion rather than being like, So in a situation like that, could you potentially try to replace the warping, the learned warping, with something that uses odometry information if you know the precise extrinsics of your camera at all times, or is that sort of missing the point in some other cases?
Yeah, I think for generic optical flow, you might missing information for other sequence. But if you want to develop some like application specific like flow, if you know it's like ego motion, it's a majority is ego motion, I think you can build in the information to the network. I think that will likely lead to better model, smaller model for this particular application. Yeah.
Thank you.
Yeah, thanks.
So did you do something particular to get it working for the different data sets? Like, did you like train, like mix the different data sets, or did some different augmentation for different data sets?
So
to make it work for the robust vision challenge?
So it's the same augmentation. It's applied to basically we use 3 datasets: Intel, KT, and HD1K. Yeah, and we combine all the data sources together. Yeah.
I wonder, have you tried with a data set from the field, for example, from security cameras when you record the real data? Often the times there are unwanted motion like shadows moving, lighting change, which isn't what people are interested. For cases like this, I wonder if you have any number or have any recommendation how to improve it.
First, I haven't tried it,
Okay,
but
yeah,
it would be good to first see the result and see what kind of the error it make, and then based on the error, we can decide how to improve the network for this particular scenario. Yeah, but I think if you have the training data, it's very likely it's going to adapt the network to this specific scenario.
Okay, we have time for one more short question.
Yeah, one more question about the way you do for this challenge. So all the data sets they have all this different number of images, and Kitty they are sparse.
Yeah.
And then Cynthia has more images than Kitty. And then do you do any balancing inside of this?
Yeah, we did balancing. So for each iteration, we take image from each data source equally, equal weight from the 3 data set.
Oh, so in 1 minute batch you have image from different data set, or is
from 3 different data set.
So you don't do any work use the Middlebury data set?
No, we did not use the Middlebury. Yeah.
Okay.
Just Intel, KT, HD1K.
Okay, I see. Okay, thank you.
Okay, let's thank the speaker again.
Okay, thank you.